Hey guys, my name's Gary. I'm one of the LAs for your 5B course. I just wanted to go over this problem number 3 on the second on week two's discussion worksheet, only because it was a little bit difficult, and I figured I'll work through it. There's quite a bit of confusion among the students, so I'm just going to go over how to think about this problem so that it actually makes sense. Okay, so for part A, it's asking us to draw a graph of the temperature of the ice and temperature of the surrounding water versus time. Hint: the ice and surrounding water will be two separate lines. Okay, so this part A is already kind of confusing, only because you can't really draw the graph of the temperature in ice with separate lines like the one up here. You can't draw a graph like this unless you actually know where the equilibrium point is, which is, found in subsequent parts of the problem. So that doesn't really help us. But what we can do is we can actually draw a diagram, a phase change diagram with respect to energy instead of time, like this one we have over here on the bottom right, okay? And this is going to help us out a lot. So part A is kind of taken care of. I'm just going to draw it as this graph right here. I know it's a little bit confusing, probably just poor wording of the problem, but just bear with me. We first need this phase change diagram right here. This is a pretty standard phase change diagram. So first I'm going to draw the respective components of this diagram. This sloped portion right here is referring to the change of, here, I'll just label each of them in green. This part right here is the ice, right? This ice is increasing in temperature from -2 up to 0. And it's still complete full ice. So say I had 400 grams of it, this entire time I still have 400 grams of it, right? Now over here, this is the part of the phase change diagram where the temperature of the ice and water mixture is staying constant at 0. But energy is being inputted or being lost, depending on if you're thinking of the water or the ice. So in the case of the ice, the energy is being inputted into the ice from the water, but the temperature is not changing. So over here, this entire part, ice is melting the entire time. And then finally, at this point right here, this is the point where all of the ice is melted. Okay, so it takes some amount of energy, specifically Q1 over here and Q2, to melt all that ice. Okay, so for part B, assuming it's an isolated system, what is the final temperature of the system? So when it says isolated system, what it's trying to say is there's only two things, quote unquote, in the system: the water and the ice, right? So any energy that's being inputted into the ice to increase its temperature is being given by the water. So as our temperature is increasing, as our energy is increasing as well, that energy is coming from whatever the water is giving. So as the water decreases in temperature, the ice increases in temperature. Now the question is, what's happening? Like, where is this going to end on this graph? Is it going to end somewhere here? So say, is the final temperature going to be like 20 degrees? So the ice barely made the water warmer and it just all immediately got melted? Or is something in the middle going to happen where we're going to end up at 0 degrees with some ice water mixture? So some of our ice melted. Or are we going to end up in this region right here where our ice was so, I guess, impactful in our system that it froze all the water that was originally at 21 degrees? So we're going to figure that out. The first thing we're going to do is think about where the energy is coming from to melt this ice. The energy is coming from the water, right? So say I drop the water down to, 10 degrees. Oh, also, this y-axis is obviously not to scale. If this spacing right here is 2 degrees Celsius, this spacing right here is obviously not 2 degrees Celsius. So just bear with me. If I were to draw this to scale, I'd have like the 21 all the way up here, which, is just inconvenient. So again, as I drop in temperature and give away some energy from the water, I'm giving it to the ice and I'm trying to bring it to some point. Okay. So again, for part B, let's try and figure out first how much energy it would take to melt the ice. Okay. So that would be the energy to get it to this green point right here, which would be Q1 plus Q2. Okay. So first we're going to figure this out. Well, Q1 is just going to be mc delta t. It's going to be that equation because all the sloped areas are given by that equation. And this middle section is going to be given by this equation. Mass times the latent fusion constant, right, for water. And we're going to see how much energy this takes. Okay, so for that part, I already have the values over here. It should be 0.4 times 2090 times 0 minus -2, so 0 plus 2, aka 2, and then divide that by, this gives us a value of 1.7 kilojoules. Then I'm going to add that to this part of the equation, the latent fusion part, which is 0.4 times 3.33 times 10 to the 5, which gives me 133 kilojoules, which gives me a total of 134.7 kilojoules. So let's try and, just step back for a second and ask ourselves, what does this energy mean? This energy is the energy it would take to get to that green point right there. So the water, Q3, would have to be enough to get, would have to be exactly 134.7 kilojoules to get us to that green point. So let's see how much energy that water can give. Let me actually keep that circled. Let's figure out how much energy the water can give to get down to 0 degrees. So let's call that Q3. I've labeled it Q3 over here. So Q3 equals what? Q3 is just going to be the MC delta T equation for this slope right here, to bring it down all the way from here until here. So let's figure out what that is. That's going to be 1 kilogram times the specific heat capacity of water, which is 4190, times 0 minus 21, which is going to be negative. And this is going to be a value of negative 87 kilojoules. Okay, so clearly this is not going to be enough because any energy that I input into my ice is going to come from the water. So the maximum energy I can give to my ice is this much to get to 0 degrees. Okay, and 134.7 is it's just a theoretical number. It's the amount of energy I would need to get to this point. But I don't exactly have that much, right? So my final temperature is going to be somewhere between 0 and -2. I'm never going to get to this point to pass 0 degrees. So I know my final temperature is between -2 and 0. Now, I still have two options. I could be at 0 or I could be less than 0. Let's ask ourselves if we can be anywhere less than 0. Did the amount of energy that the water can, or is the amount of energy that the water can give able to get rid of this little bump right here, this area right here? Is it able to do that? Well, Q1 we found out was what? What's this energy right here? Q1 was 1.7 kilojoules, right? That part's pretty easy. We already found that energy, and our energy of 87 kilojoules can easily take care of that. So using just some balancing of our I guess you could say the amount of energy we have to use versus how much we spend. We have 87 kilojoules to use. We spent 1.7 kilojoules of it. So how much is left for us? That's 85.3 kilojoules. Oh, I just realized I didn't really answer the actual answer for part B. I kind of made an assumption. So once we get past this Q1 hump, which we easily did because we had 87 kilojoules to give from the water, and we only needed 1.7 kilojoules of that 87 to get past that bump, but we didn't have that remaining 133 over here to get to 0 degrees, or to get past 0 degrees. So we're stuck somewhere on this axis, somewhere here. We're stuck somewhere here. So our final temperature is naturally 0 degrees. So the answer for part B is going to be 0 degrees. It's kind of a trick question because it's, trying to test your intuition for energy given and energy used, and that it's all going to be equal between the water and the ice. Now for part C, this is where it gets a little more tricky. What is the final mass of ice when the system reaches equilibrium? What is the final mass of water when the system reaches equilibrium? So for the final mass of ice, we have to ask ourselves, once it gets to the 0 point right here, it's still 400 grams of ice. 400 grams of ice. But after we used up the amount of energy to get past this bump, we used up some more energy that the water could give. Because the water wants to come down to 0 and the ice wants to they want to equalize at some point. They're reaching some equilibrium. So however much energy this water can give to get down to 0 is what is given to the ice after it reaches this Q1. So that might be a little complicated, but let's think about it this way. We only have 85.3 kilojoules left of energy to melt the ice starting at 0 degrees. Okay? So starting at 0 degrees. So using our equation, Q equals the mass of the ice times the latent fusion equation, the heat of formation, we can calculate how much mass is going to be melted. Okay? So for Q, we have 85.3 kilojoules which equals the mass, which we're trying to find out, times the latent fusion, which is this equation, right, which is this number right here, 3.33 times 10 to the 2. This gives me a mass of 256 grams. Okay, so this number is actually the amount of ice that is melted. Melted ice. So if we started off with 400 grams of ice, we melted 256 of it, and we are left with 144 grams of ice. Right, we're left with 144 grams of ice, and we initially started off at 1 kilogram of water, and we're going to add 256 grams of that to get our final amount. So 1.256 kilograms of water. This makes sense because any of the ice that melted turned into water, right? Hence the melting part. It turned into water. So any ice lost turned into water. So we lost that much and we gained this much. I'm not sure what units the problem is asking for. It doesn't even ask for units. It doesn't really matter. The general idea is that you get this. So yeah, that's the important part. The important part is to realize that the amount of water, the amount of energy in the water that you can use is the only amount of energy that you can input into the ice, right? So we can only input 87 kilojoules of ice of energy into the ice. We used 1.7 kilojoules of it to get past this hump, and now we're in this region. Once we're in this region, it takes 133 to melt all of it, but we only used about 85.3 kilojoules right here. We only used 85.3 kilojoules, which gets us at about a third of the way there in terms of energy. But again, the temperature this entire time is at 0 degrees. Okay, so I hope this helped. So the final answer for this is ice equals 144 grams. Again, you can have plus or minus some numbers here. I don't care if you get 141 or 148. That's not that important for me. And then for the water, you get around the same, just added the number, 1.256 kilograms. 1.256 kilograms of water at the final temperature, at equilibrium. Okay, guys, hope that helped. Just comment on this Piazza link if you guys have any more questions, and thanks for watching.